So after we constructed our parsing DFA and converted it to a table, how can we actually use this? So this here is our LR parsing algorithm, and our LR parsing algorithm actually starts in a very simple way. So it pushes the end of our input and pushes our start state and reads our next word into a variable called word. And now we have an endless loop that can only be exited when we've successfully finished parsing. So what it does is first it takes a look at the top of our stack and copies this into state, and then checks if there is an action with the current state on the top of the stack and the next word that we're going to read that we've just done here initially. If some of this action is an R action, so a reduce action that reduces a non-terminal symbol alpha to some production beta. Now if this is the case, then we'll pop the production from our stack. So we'll pop 2 times the size of beta symbols, because we always have a terminal symbol and a state on the stack, so always 2 elements on the stack for one of the symbols in our production beta here. Then we set our state to the new top of the stack after we've popped our symbols. After that, then we push the left-hand side of our production, so the non-terminal symbol A, and then we add this goto as the information on where to go next. So we push goto to this state, that's just top of the stack, and A onto the stack. So if we find another action for state and word that is a shift action to SI, then we simply push the word and the state, and then we just read the next word. Finally, if there's an action for this state and word that says accept, that's our way to successfully leave our loop. So we break out of a loop and we end up here returning success only in case we ended up at this accept condition here. And if none of those actually can be fulfilled, so if we don't have reduce or shift or accept, so essentially some empty cell in our table for our DFA, for our LR parser, then there's a failure. So something must be wrong with the input stream. It's not a word of our language. So what we do here is we use a symbol stack and a state stack, and the current state is the top of our state stack, and we push state 1 to our state stack, and then we perform an action for each token. In case of shift, we push the token to our symbol stack, like here or here, push our state to the symbol stack, and then the current state is S. In the case of reduce, we remove all the symbols on the right-hand side of the production from our stack. We push the left-hand side symbol of our production, maybe here, here, and here, and then we pop the same number of states, and then we take the new top of the state stack, look up in the table what is actually an entry for the new top of the state stack, and our left-hand symbol X, we push S2 to the state stack here, and the current state is S2, and in case of accept, we just report that we've successfully parsed the input. So let's see how to use our LR DFA parse table now and the algorithm to actually parse a real input string. So here's our parse table again for that grammar we've seen above, and we want to parse this input string ID plus ID and then the end of the input. So we start at state number 1, and our symbol stack is empty at the beginning, so we'll see the complete text as the input here. And so the next symbol is ID that we see here, and we can look it up in our table. So when we are in state 1 and read ID, we do a shift and we go to state 4. So essentially what we do is we remove the first token here from our input stream, push it on the symbol stack, and we moved to state number 4. Now what are we going to do in state number 4? State number 4, our next input token is a plus. So state number 4 and plus means we reduce the left-hand side according to production P3, which is that one above here. So it reduces an ID to a T symbol, and that's exactly what we do here. And we end up in state 3 then. So the next thing we do is, well, we have a T and a plus. So essentially what we do here in state 3, when we see a plus, we go to state 5 and we shift once more. So we shift our plus onto the stack. So we're now in state 5. In state 5, we see an identifier that's coming up. So the next thing we do is again a shift operation, and we'll move back to state 4. So we shift 4, we have T plus ID on the stack, and we have added state number 4 to our state stack. So now we can see what happens now. So essentially we're in state 4 and we see a dollar. So the next thing we have to do is we have to reduce according to production 3 again. So reduce this ID to a T and replace the 4 by 3 on our state stack. So we're left with T plus T. So now again we're in state 3. We read a dollar again because that's the remaining input, because there's no input left. So now we reduce according to a different rule, according to rule 2. So we reduce a T here, the right hand side always, with an E. And then we end up in state number 6. And state number 6 now leaves us with T plus E. T plus E, we've seen, if we read a dollar, means we reduce according to production number 1, which just reduces T plus E to our E symbol here. And if we read an E and a dollar, then we know we're in the accept state and our parsing has successfully finished. So now let's look at a different example. So this grammar here is different from the one in our previous example. So now we want to write expressions that can contain an identifier, and the identifiers can be combined using a plus or a multiplication sign. So we have to change the DFA a bit. So one part of the DFA would actually to have this rule here. So in state 3, you either have this one here, you're reading an E, then your input is here, and then you can read a plus E at the end. Or you're reading an E, and you have already read the multiplication side and an E, and you're here, and then the next plus can be coming. So we add some states to our parse table here with 3 and plus. And this gives us, well, this information here. So if we're in state 3 and we read a plus, well, now we can either do a shift or we can do a reduce, because we're at the end of the second rule here. So obviously there's a conflict, because we need to decide here if we need to shift or we need to reduce according to rule 2. So this is a classical shift-reduce conflict, which means our grammar is ambiguous. And in this case, we can resolve the conflict by selecting one of both actions here. Question is, of course, which one. So to understand which one, you need to think about what the top of the stack now looks like. So think about what will happen later if we take the shift rule, or if we take the other path and select the reduce rule. So if you try to hand over this grammar to a parser generator, this would be the example parser generator output. So it gives you a warning, and it says there is a shift-reduce conflict on plus, and it resolved this shift-reduce conflict by selecting the shift action. So essentially it gives you the context here, what happens, and it gives you the rules that it could choose. So context lists exactly the LR items in the conflicting state and shows you what's going wrong. And if you then change the formatting a bit, then you can align the dots in the state and you can see where this actually leads to. So either you're at this position and you've read already exp plus exp, or you've just read a single exp, you're at this position again, and then you could read plus and exp. And the top of your parse stack might look like this. So you have something on top of the stack, then exp plus exp. then you're here, and the remaining input would be another plus and another expression. So this leads to two different parse trees depending on if we shift or if we reduce. So if we align the dots, we know either we've read a complete sub-expression consisting of two expressions and a plus, or we only read the first part of an expression and there's an upcoming plus and an expression. So either we have this tree here, so we've already seen this one, and the next expression is our sub-expression we're going to read. That happens if we shift. Or if we already reduce in the beginning, we get the syntax tree more or less the other way around, so it looks a bit mirrored here. So we have the first expression here as the inner one, and then the second expression here as the outer one. And the question is, which rule should you actually choose? So what are the different kinds of conflicts that may actually show up here? So one thing we've already seen is that we might have a shift-reduce conflict, so we need to decide if we need to shift and read another plus, or if we can reduce this complete rule here when we see a plus is upcoming. Another conflict may be if you have two rules like this here. So you have two productions where you have a non-terminal symbol C as the last thing, the rightmost thing on your stack, which means when it comes to reducing and you have the same following input symbol T, then you could choose either to reduce just this C to a D, or something that has a sequence BC, and you could reduce this to an A. So there's different ways to resolve these two problems here. So shift-reduce conflicts can sometimes be solved using precedence rules. We've seen these before for ambiguous grammars. This particularly works well for binary expressions with priority and associativity, so if you're doing arithmetic operations and similar. So for other cases, you need to really carefully look at the shift-reduce conflicts that are complained about by your parser generator to see if some precedence rules are actually applicable here, so if there can be some predefined order of evaluation of whatever you're going to describe in your grammar, or maybe if this is not the case, you might need to change your grammar. For reduce conflicts, on the other hand, you need to think through the problems and change the grammar, because that's a problem, well, that might lead to very different outcomes, obviously. So maybe even one thing leads to a successful parse, the other one not. And so you have to think through what's actually going wrong and change your grammar accordingly. So this is an example for typical precedence rules for an LR expression grammar. So we have a grammar like this here. So again, some sort of expression grammar with a comparison operator, an exponentiation operator, are four arithmetic operators. And an expression can also be an identifier or an integer. And of course, you see you have very many conflicts that can show up here. So the precedence rules might be derived from arithmetic rules like this. So you have a right precedence for the power operator here. You have a left precedence for multiplication and division. You have then a left precedence for plus and minus. And then you have a non-associative operator equals, which can be switched around. So the precedence rules are actually interpreted in the order that they are written in the grammar. So this is an example from a parser generator grammar for YAC exactly. And shift-reduce conflicts can now be automatically resolved by reading these and using these precedence rules. So operators in the same rule have the same priority. So plus and minus have the same priority. And times and diff again has the same priority as the other one. Operators in an earlier rule, so a rule that's further up in the list, have a higher priority. So power operator has a higher priority, for example, than your plus operator. So how do these precedence rules actually work? So a rule is given a priority and the associativity of its rightmost token. And if we have two conflicting rules with different priority, then we choose the rule with the highest priority. So in this case here, if we have two rules, E can derive E, current input symbol, plus E, and an arbitrary following symbol, or we could do a reduction here. So by using E, can derive E times E, and then the end is here, and the plus must be coming next. Then we would choose reduce because of the higher priority of the multiplication symbol here. And on the other hand, if we had a grammar like this one here, if we had two multiplication symbols here, then we would choose shift, because obviously a multiplication symbol has the same precedence as the other multiplication symbol. So if we have two conflicting rules with the same priority, then they have the same associativity. Left associativity favors reduce, whereas right associativity favors a shift operation. If we have non-associativity defined, then this removes both rules from the table, which means that any input following that pattern would cause a parse error. So in the left example here, we would choose reduce. In this example here, using the power operator, we would choose shift. And in the right example here, because of the non-associativity, we would choose no rule, because we wouldn't know what to do, and we would output an error message. So this LR parsing approach we've seen here was an LR1 parser. This is a general class of parsers, and this LR parser class is a bit bigger. So essentially this number here, as with the LL parsers, indicates the amount of look-ahead. So how many tokens, how many symbols of our input do we need as look-ahead to decide about the productions in our grammar here. So in theory, you could build LR0 grammars which don't have any look-ahead. They're not very useful in practice. Then we can have very simple LR grammars that only look at the follow set to decide where to put reduce actions. These are somewhat useful for some useful grammars, but not that common. Now there's a subset of LR1 grammars which is often used in practice, and LALR1 grammars actually tries to move to merge the states that have the same LR terms but different look-aheads. So the idea behind this is that parse tables for real-world grammars, so not our small examples here, for LR1, if we construct them, can get very, very large. So they consume a lot of memory, they take a lot of time to look up, and so on. And using this combination of states, this merging of states in LR1, this leads to much smaller tables, so to more efficient parsers. This LALR1 subclass of LR1 parsers or LRK parsers is used by most well-known compiler construction tools like YAC, which we're going to use, and a number of different ones which we've listed here. And this is actually sufficient for most practical parsing problems. The real LR1, which we've described here, is slightly more powerful than LALR1. It's not used in practice due to these very large tables, and if we want to have tables with even further look-aheads, so LRK in general for k larger than 1, we have even larger tables, and this is impractical even if we could parse a bit more on some more language structures using LRK with k larger than 1. So different versions of LRK parsers can be used with grammars of different complexities. So this is essentially just a look at a part of the Chomsky hierarchy we've seen before. So we start with LR0, which has a very small and almost useless set of languages that it can parse. SLR has a bit bigger one. LALR again has a bit bigger one. And then we have the unpractical things like LR1 or LRK. And still we can have additional grammars which are unambiguous, and then we have this part to the right here, which would be ambiguous grammars, which would be very difficult to parse. Still, all of these are context-free type 2 grammars, so this is just one of the elements of the Chomsky hierarchy, and you see even inside of the context-free languages you can have different variations. So if we compare LLK versus LRK parsers, so top-down versus bottom-up parsers. Let's first take a look at the naming. So the first L always means it parses input left to right, so that's the L here and the L there. The derivation for LL is leftmost, whereas for LR it's rightmost. The look-ahead is always K symbols, so for example 1. The tree for LL is built top-down, for LR is built bottom-up. LL selects the appropriate rule after seeing the first k tokens, whereas LR parsing needs to see all of its tokens plus some additional ones. LLK is not happy about left recursion, whereas LRK can work well with left recursion, so it's easier to write grammars for an LRK parser. We don't have an unlimited common prefix in LL, whereas that works with LR. The resolving of ambiguities through rule priority, for example, works for the dangling else problem. And in LR, we can also use associativity and priority rules to resolve ambiguities for the shift and reduce conflicts. Error recovery in LL parsers is very often only trial and error, so maybe the syntax error messages that you get from an LL parser might not be as good, or it might just be more work to actually figure out where your parser actually has found the error. Whereas error recovery for LR parsers is pretty good, so there are a number of good algorithms for this. We won't go into details about error recovery because that really is not part of the introductory lecture on compiler construction. And finally, if we want to implement an LLK parser by hand, that's entirely possible, and we've seen examples for this, and there's a very easy construction by using the recursion and providing a simple recognition function for each non-terminal symbol on the left-hand side of a production. And for LR parsers, this is just too complicated, and you should use a generator, and this is of course what we're going to do in the upcoming examples. So finally, we can compare LL versus LR grammars here. So you see the amount of look ahead essentially determines the complexity of the language that it's able to parse, and you see the subclasses LALR and SLR have no direct representations for top-down parsing here, and LL1 parsers, so just LL top-down parsers with one element of look ahead, can detect languages with the same complexity as an LR parser with one element of look ahead, and the same for K element of look aheads. And then of course you have the other grammars around here, but still all of these are just context-free languages in our Chomsky hierarchy. So what's next? We're right in the middle of parsing, but we haven't written a single parser yet. We've just had a look at the theory behind it and had a look at how to, in theory, build these tables, and had a look at the algorithm. So now we will take a look at practical considerations to construct parsers in the upcoming lecture. We will give an overview of parser generators, especially the YAC parser generator, and of course we'll give a number of examples for this, and especially important, of course, the interaction between parsing and scanning, so between the YAC tool we're going to introduce and the LEX tool you already heard about in previous lectures. That's all for today. Thanks for listening. Until next time.